A very good afternoon to all of you. So we are going to start with the problem solving session for the week 9 of the course Advanced Soil Mechanics, which has been taught by Professor Srideep Shekharan, who is a professor at IIT Guwahati, and I am the teaching assistant for this course, Mujibur Rahman. I am from the Department of Civil Engineering, IIT Madras. So in the week 8, if we talk about a simple, like a brief recapitulation what we did in the last week, we have went through the stress bar representation for the drained and undrained test, different cases we saw. Like we saw the case for the drained compression, how we can impose like the compression in the sample. Then we studied the extensions also in the drained and undrained case. Also, we went through the how we can plot the total stress path and effective stress path for the both drainage for the different drainage conditions, and how the initial state and the initial stress history or K naught condition is affecting the stress plots. In this, I mean, so how the strength is varying due to the change in the cohesion values, or if we have the different initial state. After that, we have seen the like in the last lecture we did some like field cases also. So we'll be extended that field cases in this lecture also, in which we will study the stress change beneath foundations, and also the same thing for the retaining walls. Then we will be going into the next module, that is the critical state soil mechanics. So starting with the stress change beneath foundations. Like if we have a foundation like this is the foundation which is imposing some load on the soil sample, and this sample is placed, or we have to consider this sample, which is totally at the center of this footing and at some depth. The reason for this is if we take a sample away from this, it will have the components for shear also. So keep the thing simple. We are consider the sample of the soil which is lying directly beneath the foundation at its center, so that there is no eccentricity between the load and the sample that we have considered. So due to this foundation stress, due to this when we have considered this foundation and it will impose some load on the foundation, there will be the axial stress sigma A and radial stress sigma R. Now at this point, the sigma A will have a overburden plus the load coming from the foundation. Fine. And if we consider as the K naught condition, fine. So this sigma R will be less than the sigma A. And this will be a typical case of a compression which we have studied in the last few lectures. So loading from the foundation increases the stress developed in the site. And as I told you, this sigma A will increase with the loading because it is going to increase the stresses in the soil. And this is the total. If we plot this stress conditions in the T and S plot, P represents the like the initial consolidation state, and P dash represents the initial consolidation state in the effective parameters P dash, and U naught is the initial pore water pressure, and the difference between the TSP and ESP, effective stress path and total stress path, will be equivalent to the initial pore water pressure. Now, TSP is P dash Q dash corresponding to undrained loading, that is true. This PQ is the total stress path, and P dash Q dash is the effective stress path in the undrained condition. And ES effective stress path will depend on the soil characteristics, and it will also depend upon the stress history. As we have seen in the last lecture, how the ESP effective stress path are going to change with the A parameter, which is actually considering the stress history, and also we see how the soil characteristics are affecting the effective stress path. So again, we have to repeat this in this again and again in order to understand the things that ESP will not, like it is a dependent parameter and which depends upon the soil characteristics and stress conditions. Now, if you see that once we construct the foundation, what will happen that there will be the generation of excess pore water pressure. Fine, the conditions will be undrained. It is as like as you are constructing the building, and the surrounding soil will experience this load in a short duration of time. So the loading condition will be a undrained, or the drainage condition will be undrained. So in that case, there will be the pore water pressure, generation of excess pore water pressure immediately after the consolidation. So initial excess pore water pressure is positive. It means that due to since the pore water pressure that is being built up due to the construction of the foundation, there will be the decrease in the effective stresses. Why? Because we know that effective stress is equal to sigma minus u. Since u is since I will write it like this. Sigma dash is equal to sigma minus u. Since due to the increase in the loading, this u will increase. Pore water pressure is going to increase immediately after consolidation, which will reduce the sigma dash, or we can say the effective stress parameters are going to reduce. Now you can see how the ESP is varying due to the loading. So at each point of time, like for example here, you can see if I will draw a line here. So let's assume this. This was the ESP. ESP if we have done the drained, if we have started the drain test from P dash. Since it's the undrained condition, and this is always it will be a U naught initial pore water pressure, and you can see how the undrained conditions are changing the pore water pressure. So at each point of time, the U is increasing. Fine. Now it reaches up to a certain point P. After that, what will happen? Like this pore water pressure will tend to it will start dissipating. Fine. Now when this pore water pressure will start to dissipate again, when the pore water pressure will start to dissipate, what will happen? That there will be increase in the stresses. Fine. So sigma dash is equal to sigma minus u. When pore water pressure start to decrease, means dissipation means it will start to decrease. What will happen? This sigma start to rise up. Fine. So there will be increase in the effective stresses. Fine. So that's why you can see that at up to this point, there is an increase in the pore water pressure, which actually decreases the mean effective stress, brings the soil towards the failure. Now, the amount of the space, you can see some up to here, the soil has reached. So this gap here will govern the factor of safety for the soil in the undrained case. Fine. Now, what happens after Q dash? After Q dash, after sufficient amount of time, when we have constructed the building, the pore water pressure starts to dissipate. When it starts to dissipate, we are not changing the external loading. So what will happen that our stress path will move towards the right without the change in the stresses T. Correct? So our mean effective stress starts to rise because the excess pore water pressure starts to decrease. Now let's assume at R dash the soil has reached the equilibrium state. Fine. So UF is the final pore water pressure. So it means that during the like when the pore water pressure starts to dissipate, there is an increase in the S dash, correct? And at this final UF, it can be equal to U naught or it can be slightly uh, like smaller than this. Now the foundation will fail. The foundation will fail if Q dash touches the failure line. Yeah, this is true. Like if the stress. Hello. Okay. I will repeat it. Wait. Yeah. So I will repeat from here again. It's not an issue. Yeah. So So from here, what will happen due to the generation of excess pore water pressure, our effective stress path will move towards the left. Fine. And we have a bound here. We can't go beyond this KFC. Correct. So up to Q dash, the soil is going like if we like if the soil has stopped at Q dash, it means that it has some allowance to reach the failure. It means that foundation has a tendency to fail if this Q dash touches this failure line. Correct. So distance from failure line represents the factor of safety. That's what I told you. This is the margin from here to here, from this point to this point, will determine your factor of safety. Now, what is happening in this case for the foundation case, as the pore water pressure is getting dissipated with time, this effective stress path moves to the right. Is it's going away from the it's going away um, from the failure line. So it means that when it's going away from the failure line, it means that the factor of safety is going to increase with time. So fine. So factor of safety of foundation under undrained condition increase with time. Correct. So our factor of safety will increase now because the stresses are now going to effective stresses are going to increase, which has led this effective stress bar to move towards right, which is far from our failure line KFC. Fine. So due to this shift of this effective stress bar towards the right, what is happening that due to the dissipation of pore water pressure, there is the rearrangement that is happening in the soil, or we can say there is a reconsolidation that is happening in the soil. Fine. So consolidation will happen under dissipation of U excess. As the pore water pressure will dissipate out, excess pore water pressure will dissipate out, there is a chance that the soil will rearrange. Fine. So due to this rearrangement, there will be the increase in the strength. So drain loading of foundation is P dash R dash R dash. Now you can see there may be the chances. For example, there may be the chances that we will start doing the drained loading from P dash from here. So you can see that the soil, if we start the drainage loading from the P dash, the soil has enough strength in the strength till it reaches to the failure. So it may be the case that if we load the sample up to this point, the soil may settle more than the limits, or the foundation will cause a settlement in the soil, which will cause the failure of the this foundation. Or as the soil will fail, the foundation may tilt, or it may undergo the failures. So we can say that in the drainage condition, there are the chances that the settlement will be high because the soil has a tendency to take the higher load. Once this pore water pressure will start to dissipate, there will be the chances of higher consolidation. So more loading is possible in this P dash S dash, but settlement will be very high, which can make the things unserviceable for us. So in this case, while we discuss the stress change beneath foundation, we have seen that once pore water pressure starts to dissipate, our factor of safety starts to increase. However, if we start doing the drain loading from P dash, then the soil has a tendency to be loaded to a higher stress. But once since it's a drain condition, there can be the higher rearrangement, higher volumetric strain, which can impart the high settlements or more settlement in the soil, which can make this foundation which is being built up on the soil unserviceable. Fine. Now, second case can be the stress change near the retaining walls. Now, two things can happen in the like if we talk about the retaining wall, either there can be the backfilling of the retaining walls, or there can be the excavation in the retaining walls. So, in both the cases, the effective stress path and total stress path will help us to know that which failure condition we need to consider. Right? So, it helps to understand whether short-term undrained or long-term drained condition are more critical. So, the main aim of doing this exercise is to know if we are going to construct a building or if we are going to do the backfilling. Do we need to consider the short-term undrained strength, or we need to consider the long-term parameters like long-term phi or c values? So this is the main practice of doing the this exercise of plotting the stress paths considering different situations. Fine. So for retaining walls, shearing caused by excavation is different from shearing caused by backfilling. Now, as I told you that in the retaining walls we can have either excavation and the backfilling, and the soil can shear or reach the failure in different manners because the way the stresses are being imposed on the soil sample will be different. We will take the first case, retaining wall subject to excavation. For retaining or subject to excavation, what will happen that the active and passive case, for both the cases, total stress path will be negative. Why? It has been like in when we have discussed that compression, the different cases for the drained case and the undrained cases, where we did that D1, D2 compression. We have seen that how we can like compress the sample in different manners. Similarly, we have seen how we can do the extension, how we can impart the extension in the sample in different manners. For example, that this is the soil. Fine, I will make it little. This is the soil, for example here, and you have to start. This is a sample of the soil in which it has a vertical and some uh, radial or lateral stresses. So sigma v is greater than sigma r because like always the vertical stresses will be greater than horizontal stresses based on the k naught consider rest. Now what will happen? For example, we have started excavating here. If we start excavating here, our radial stresses will start to decrease. Fine. So we are actually bringing the compression here, but by reducing the radial stresses, it means that our sigma is going to reduce. Fine, and sigma v is becoming constant. It's a similar case where we are doing the compression by reducing the radial stresses. We have seen that in the previous week 8 content. So in that case, how our TSP is moving? Our TSP, see, what is T? T is sigma axial minus sigma radial divided by 2, and S is sigma axial plus sigma radial divided by 2. For example, if you're not changing the sigma A at all, so our slope is becoming negative, correct? Now this sigma A is decreasing, so it is minus of minus sigma R, so it means that T will be increasing, and this is decreasing, so S will be negative. So we are going towards left side with and also like it is like upwards and left, so it will the slope will be a negative. Now that's why like you have seen that the total stress path for this case is negative. Now there is a negative TSP, and PQ represents the total stress path for the loading, and we have an initial pore water pressure Q naught, as a result of which there is a difference in the TSP and ESP. Fine. So P dash Q dash is the initial ESP. Fine. Now when we are doing this excavation, fine, what will happen? We reach point Q. Now when we are doing the excavation, we are taking the soil out. You have remember that in case of sampling, when we are reducing the effective confinement, there is a kind of a suction which is holding the sample. So similar to that, you can take that as a benchmark or a similar thinking you can consider here as an analogy you can consider here that due to this excavation there will be the generation of negative pore water pressure, and this negative pressure will try to make the things stable during the excavation. Now when the see what will happen again, if we see the effective stress is equal to sigma minus u. Now this u is negative in the sense there is a kind of a suction which is holding the sample. So this is minus of minus u. Our effective stress will try to slightly increase. So that's why you can see our pore water pressure, our the T and S plots. You can see they are not. It's not going like this. In like you have seen in this case, which is moving away from the this line or TSP. You can see it is slightly coming closer to it. Fine. Now at Q dash, we have stopped the things. We are not now like we have at the end of the excavation stage. Now what will happen again? This negative bore water pressure starts to dissipate. Fine. Now when it starts to dissipate, what will happen that there will be the generation of positive bore water pressure, which will reduce this Q to R dash. So it means that with time, if we talk about the effective stress in terms of undrained conditions, so with time this R dash will go close to this failure line. So there are the chances that there will be the failure. So failure will occur if Q dash or R dash touch the failure line. So both the things can happen. Either this Q dash will reach to this place, or once the pore water pressure starts to dissipate, negative pore water pressure starts to reduce, this R dash will reach to failure line. Fine. So if Q dash reaches failure line, failure occurs during undrained excavation. This is true because at this point of time it means that we are doing the excavation, and in case if this Q dash will reach to this failure line, it means that this failure happens due to the undrained excavation. And if R dash reaches failure, in case this R dash reaches to failure, once it has we have stopped the excavation stage, and this R dash has reached to failure, it means that the failure occurs after some time of the excavation. So it means that the here we have started the stopped the excavation, and here we are giving some like it's a kind of we have stopped the construction phase. Now we are like observing it. So now due to the dissipation of this positive pore water, negative pore water pressure, what is happening that our effective stress path will move to the left. So the failure can happen if the soil fails at Q dash, it means that during excavation only the soil has failed. If soil fails at R dash, if this R dash leads to this failure line, it means that the failure has occurred after some time of excavation. So in this case, with time, this R dash is going close to this TFC. It means that our factor of safety is reducing because this R dash is going to reach the failure state. So this was the one case of retaining wall when we have when we consider the condition of excavation. Now, if we take the case of backfilling, so what backfilling is actually, for example, this is the initial fill or initial ground level. So we are filling this, we are constructing the embankment over it. Timely, we are constructing some embankments over it. Now, due to backfilling, both stress parameters were increased. It means that due to the backfilling, when we are increasing the like stress, we are increasing the stresses in both x and y, horizontal and radial direction, horizontal and vertical. It means that both T and S or P or Q, or we can say sigma axial and sigma radial, all the parameters are increasing. Like whatever we will consider, if we consider T and S, it means that these two parameters are going to increase. Or we can say the stress parameters are, both stress parameters are increasing, right? If we look at the, now we want to look at the total stress path and effective stress path for this case where we are doing the backfilling. Now we have backfilled. Fine. So PQ is a TSP due to the backfilling. So TSP is the total stress path for the condition backfilling, fine, which will have a slope of like 1:1. Now P dash Q dash is the ESP during undrained conditions. Fine. Again, due to the generation of pore water, positive pore water pressure after immediately after this construction, there will be generation of U, which will like reduce the effective stresses. That's why our ESP will move towards the left. Now this after Q dash, we are stopping this backfilling. We have let the soil to readjust this loading phase. Now what will happen is U excess will start to dissipate. When it starts to dissipate, what will happen that effective stress will again start to gain up. Our P dash will start to increase. It will reach to R state. Fine. So it means that once we are stopping the construction phase and giving some time to the allowing giving some time to this for the readjustment of the stresses, it means that our effective stresses are increasing. Our soil state is going towards the right, which is far away from the failure line. So our factor of safety will again will increase. So that's why you can see that for retaining wall, I have told you the shearing caused by excavation is different from the shearing caused by backfilling. So this shearing caused by excavation, what will happen that it will reduce the factor of safety with time because our effective stress path is going to, if we keep it as it is, then our effective stress path is going to touch the failure line with time. And for the backfilling, what is happening that our R dash, which is the effective stress path, is moving towards the right. And you can see this U excess is the pore water pressure that has been dissipated. And after it reaches the equilibrium state, our either this UF will be equal to U naught or it will be slight difference between them. So U excess dissipates over time and ESP moves to the right. UF is the final equilibrium and distance of Q dash from failure line represents the factor of safety. Correct? So this will represent our factor of safety. So with time, this factor of safety is increasing during undrained loading. So this R dash is moving away from this failure line. So this much of allowance we have. If we reach R dash, so this much of allowance we have for the failure. So it means that with time, the factor of safety is improving, which is improving the stability of the soil. So our soil is not going to fail at this very state. So this was there were the three cases that I want to discuss with you regarding stress passes. Now, again, just a recap for the four different cases that we have studied in the drained and undrained, like that D1, D2, and E1, E2. Like we have the embankment here, correct? So initially there was the sigma 1, sigma naught, and sigma r. So due to the construction of embankment, you can see there will be delta sigma increasing in the vertical direction. Similarly, if one observing the excavation case, there is some initial delta a naught and sigma r naught. Now due to the excavation, this may decrease. Vertical stresses decrease. Fine. So this is a case of axial extension. Why? Because if sigma A naught is decreasing, and this is kept constant, so it may be the case that this vertical term may be slightly, or it may be less than the sigma R naught, as a result of which there may be a kind of a squeezing effect in the sample. Now, similar to this, we have a lateral extension where the soil sample has a tendency to have a higher lateral stresses, or there will be, sorry, if we have a lateral extension, it means that in the radial direction there is a release of the stresses as a result of the active pressure. Like this wall has a tendency to topple towards right, or it has a tendency to go the right, as a result of which our radial stresses will decrease. When we say the radial stress will decrease, it means that they can decrease decrease more than their initial values, as a result of which there may be the cause of the compression like the fine. And similarly for the passive earth pressure, where we have a lateral compression. Lateral compression means our radial stresses will be more than the actual stresses. So this can be the case for lateral movement, passive movement in the soil, when the lateral wall have this kind of passive movement. So as a result of which our radial stresses will be more as compared to our axial stress. So again we can have a squeezing effect. So these are the four field cases corresponding to that D1, D2, and D3 and D4 stress path representation that we have studied in the week 8. Now, after that, we have sir has went through this critical state soil mechanics. So, actually, when we talk about the Mohr-Coulomb failure criterion, so in the Mohr-Coulomb failure criteria, we are dealing with the P and Q stress paths. Fine. We don't worry about the volumetric strains and all. But in this model, critical state soil mechanics, we are actually considering it's actually considering all the three parameters in a single kind of a bag of Konosu model, which takes into consideration the stress, dielectric stress, mean effective stress, and the volumetric strains. So this concept was put forward by Schofield and Worth in the year 1968, and it's also called a CSSM. And what it is doing, it's actually it's integrating, or it's collecting all the information regarding the Mohr circle failure criteria. It takes into account the stress history, then soil yielding, and also the drained and undrained conditions. So it's kind of a combo pack of all the four things. It considers the MC failure, stress history, soil yielding, and drained undrained conditions. And also, it was initially developed for the saturated reconstructed clays, in which the clays were remolded and consolidated to a NC state. Now, the more important, like as I told you, it takes into consideration the stress, like P and Q, or the stress state, and also it takes into account the volumetric strain calculations. So you can see these two things. It offers a relationship between wide relationship between 2D variations of void ratio versus effective stress and versus stress and strain. So during the behavior, as a result of which, when it considers the variation of the total this void ratio and effective stress, and also the relationship between the shear stress and effective stress, it defines the behavior of the clay of specific stress history during the shearing part. Correct. So it is taking into account the stress history also, and also when we are doing the shearing part, we are able to determine it is like the stress strain and also the volumetric strain response we are able to monitor. And this model is actually combining all the three things, stress strain and E versus sigma dash plot, to understand the behavior of the soil properly, which was not there in the earlier Mohr-Coulomb criterion. So it integrates the consolidation and strength behavior also. Now, as I told you, like it has three things to do. It has to relate the P, Q, and volumetric strain. The volumetric strain can be either it can be we can consider this volumetric strain in terms of the void ratio or in terms of specific volume. So according to the critical state soil mechanics, all soils will fail on a unique failure surface which will be defined by the QP-E or QP-V space. So it means that rather like earlier it was a concept of stress obliquity where we were telling the soil will fail when it reaches the maximum stress obliquity. But when we talk about the critical state soil mechanics, which integrates the like more column failure, it takes into account the stress history also, and it takes into account the drained and drained conditions also. So we are rephrasing that criterion, failure criteria, and we are redefining that as all the soils will fail on a unique failure surface which is defined by Q, P dash and E. So it takes into account the volume change behavior in failure criterion by taking into account the void ratio and which was not considered in the earlier MC criterions. And also like for this critical state soil mechanics, as the name suggested, it has all to do with the critical state. What critical state is actually, critical state can be considered as a fundamental soil property which is dependent on the stresses that we impose on it and also on the initial conditions. Like I think in the week 7, when we are describing the stress strain plots for the OC and NC, we have seen that there is after reaching the peak state, peak stress, there will be strain softening, and followed the strain softening, the soil reaches the final state, which is called the critical state. And this critical state is independent of the initial stresses, initial conditions, which means that whether you have a loose sample or a dense sample, both the samples, irrespective of the way they will behave during shearing, they will reach the critical state. And this critical state, as I told, it's independent of the initial conditions. Moreover, this is a fundamental property. Every soil state has to reach this critical state. Now, this critical state has it has some properties. How we can say whether a soil has reached a critical state or not. That we are going to see in this CSSM concept. So when the soil is sheared, it tends to an ultimate condition called the critical state, wherein the plastic shearing or the we can say shear stresses would continue without change in the volume or effective stresses. It's like if you remember the plot, if you remember the stress strain variation for the OC, it reaches the peak state, then it start softening and reaches the ultimate state, critical state. For the low soil, it was going like this, strain hardening and then reaching the critical state. You can see this portion, this generally this part we are considering as a it's a critical state. Why there is an increase in the plastic sharing would continue without change or change in volume or effective stress. You can see even if at the constant stress, our stresses will be constant. The strain is getting, plastic sharing is getting, or the shear strain is getting like accommodated in the sample. So this is the kind of a indicative of the critical state. The soil has reached the critical state. Now, this state of perfectly plastic is known as critical state. Now, this is a plastic state. It doesn't. It means that we can't hope that the soil will come back to the initial state if we are doing a reloading in this portion. And also, generally, this critical state we are observing after like as greater strains like greater than 10%, greater than 10 to 15%. But more than different state books are referring different values, but in general, like if greater than 10%, we are considering the critical state. Now, the soil flow in this zone, in the critical state zone, the soil flows as a frictional fluid while the soil continues to deform, like it undergoes the shear strain without any change in the shear stresses, effective normal stress and void ratio. Again, as I told you, that this state there will be the accumulation of the plastic strains at a constant value of shear stresses. Fine, there will be no change in the effective normal stress and void ratio. It means that within a volume there will be the generation of the local shear kind of a shear band pockets where the soil will start to accumulate plastic strain. It will have it will accumulate plastic strain by some readjustments in the units in the arrangement of its particles that can be visible in terms of the shear pockets which you can see. Like if we are doing the testing, you will be able to observe that there will be a shear band occurring in the soil sample. So those things are actually the indicative of the this critical state. Now, another point to discuss is at critical state, effective stress, shear stress, and volumetric strain with respect to shear strain is constant. Like if we see the variation only, for example, like this and this, you can see it's a, for example, this is dielectric stress and strain. So there is no change in the dielectric stress with the strain. Fine. So the variation of this dielectric strain with the strain is zero. Similarly, our P dash mean effective stress, volumetric strain, they are not going to change. If you see the volumetric strain versus effective, like the plot between the volumetric strain versus actual strain, generally for a dense sample it will be like this. Fine. And for loose, it is like this. So it means that once the sample has reached the critical state, there is also no change in the global volumetric strain of the sample. Fine. So these are the formulations which you can just remember if someone tells you about the critical state. And generally, as I told you, we have the two representation for it. Either we can have a QP-E plane or we can have QP-V, where V is the specific volume given by 1 plus E. Now, any soil undergoing shear should finally attain a constant state. If not, it would continue to compress or dilate, which is not possible. Now, the thing is like, is it necessary that, for example, we have a soil sample, correct? Why should it reach the critical state? What is the need of the soil to reach the critical state? Or is any state possible beyond the critical state? The thing is like, if you have a volume, like you can consider a small box where we have the jellies or something where we used to put the jellies in it. So if you are going to compress that, even if like if you first fill it with few jellies, few toffees, like 56 toffees, if you're going to compress that at certain amount of time, you won't be able to compress that. Fine. So this is the even if there will be large amount of compression or large amount of axial strain that will get or a kind of a large amount of change in the height due to the application of load in that toffee box. But if we fill that toffee box with 200 300 toffees and start to again start to compress it or load it, so it means that after a certain point of time, you won't experience any change in the stress state. Why? Because it has reached it is final packings. There won't be any readjustment in the voids. There won't be any readjustment in the position of the particles. So this state is the final state which a soil can achieve. And after that, we can't expect a state after the critical state because this is the final position or final arrangement that a soil can have. After that, we don't or we can't expect a state beyond that. Now, after that, this is taken care by defining the critical state concept where soil reaches a constant state. Yeah, as I told you, it's a constant state which after which we can't expect another state of the soil. Critical state is attained at shear stress greater than 10%. As I told you, there are different books which will have different values, but as per the notes, as per the lectures of Professor Sridhar sir, so I will go with that. So critical state is attained at shear strain greater than 10%, and soil gets reconstituted by shear strain. As a result, soil loses the track of initial conditions and achieve a unique critical state. It's very important. What happens that after 10% axial strain, when you are loading the sample, what will happen that there will be the reconsolidation of the sample. After 10% of the axial strain, what will happen? There is a reconsolidation of the sample. So whatever be the initial condition, like whether you have consolidated the sample, sorry, whether you have taken the loose sample or dense sample, or once it has reached the critical state, start reaching the critical state, its initial condition is getting lost because there is a reconsolidation of the particles or the reconsolidation of the soil, which erases the initial condition, which erases all the history from what it has experienced in the past. As a result, there we will always achieve a unique critical state. That's why we are telling for a for a particular soil sample, irrespective of the loose and dense condition, the or irrespective of the initial conditions, there is the reconsolidation that is happening after 10% of axial strain, which actually erases the stress history of the soil. It erases the effect of the initial conditions, and we will get a unique critical state. So, since critical state is independent of initial state, it is reasonable to consider it as a fundamental soil property. Fine. So this is obvious that if this is a this critical state is actually it's independent of the initial conditions, we can consider it as a fundamental property to study the different parameters or different aspects of the soil. Yeah, this will be clear from this point. For sands, critical state and residual state are the same. Yeah. Now, general representation. As I told you, I have shown the plots also. You can see that this is for the tau stress strain representation for the sand and clay. You can see that for sand, if I talk about sand first, after reaching the peak, it has achieved the critical state. Fine. So it means that from here it doesn't have that much of strength to hold the stress. But in case of clays, despite that it has reached the critical state, there is some stress which can be mobilized. So as a result, you can see we can expect a residual state in the clays which is well below this critical state. Fine. And here, as I told in the here that critical state in the flow is a kind of a turbulent flow. But here the in the residual state of the clay, it can be considered as a laminar. The particles move very uniformly to their with each other. But in the critical state, there will be a turbulent motion of the particles. It's a random motion of the particles. Right? The critical state is achieved at strain greater than 10%. We can see from here we can expect the critical state to occur. For sands, critical state and residual states are same. Fine. For soils that can go past the critical state can achieve the residual state. So in this residual state, we can have the same properties like there will be no change in the mean effective stress, divided stress, and the volumetric strain in this residual state also. But we are more interested towards the in the critical state. Now we are moving a step ahead in developing the relationships for the stress P, Q, and the void ratio. So, a few basic things we are going to develop here, which will be helpful in the next module or in the next week lectures. So, first, we are going to recap the lecture notes for this topic. Relationship between the shear stress, normal stress, and the void ratio at the critical state. Now, this is a typical stress strain plot that we have seen in the previous lectures also. Here, earlier it was a failure line, now it's replaced by a 5 days critical state. It means that this tau and C corresponds to a critical state. And this is a critical state line, and this tau can be written in terms of critical state line. Tau is equal to sigma times tan of 5 days CS, correct? We can write it? Yeah. After that, we have the E versus sigma dash plot, which is the void ratio versus the like the effective stress E versus log E versus sigma dash for the critical state. Like if we are doing if we have like for example we are doing the testing, we have taken a one void ratio and start doing the test. So with the test, the mean effective stress will increase, and as a result of which there will be the consolidation of the sample. E will change. So at final this effective stress at final value of the sigma dash, what is the E correspond to the critical state? We are considering those points only. So E critical versus the sigma. What is the final sigma at which you are taking the value for E to be a critical state value? So we have plotted those. Fine. This is actually the E critical for different values of the stresses that has been like achieved in the test. Now at a certain some value like sigma dash CS, we have the ECS void ratio corresponding to this stress ratio, this effective stress, and also this shear stress corresponding to this effective stresses, and ECS represents the void ratio at this value of the stress. Now it's all since it's a non-linear plot, correct, it's always advisable to like if we want to have a linear variation and to account for the large amount of stresses sigma dash, we can take a log plot. So this is E versus log sigma. This is the CSL line, and this is the normal consolidation line. Generally, you will get from the consolidation like we are doing the loading. There we can get this line. The slope of this NCL normal consolidation line is CC, and it's parallel to the CSL. Now for both CSL and NCL, slope is same as CC. Correct. Now the thing is, we want to develop a relationship between these three parameters, tau, sigma dash, and E. For example, if we take a stress corresponding to a very low stress state, let's assume 1 kPa, fine, 0 we can't take because it's in log plot. So at that very small amount of stress, at that state, our tau f is equal to tau cs given by sigma dash cs tan of phi dash cs. Fine, this is correct. Tau is equal to sigma tan of phi dash. Now at critical state, ECS. Let's assume that at this stress state, sigma is equal to 1 kPa, we have the E at like E critical, the void ratio at the critical state for this 1 kPa is E gamma, and it has an initial E naught of E naught is a like the initial void ratio at this stress. Right? Now we want to determine the tau cs and the ECS corresponding to this. Now tau cs is like if you know the phi cs, this tau cs is straightforward. Tau is equal to sigma cs tan of phi ds. Now this ECS can be determined from the E tau value and the slope of this line. Fine. Now this ECS void ratio at critical state will be equivalent to E tau, fine, minus Cc log of sigma dash Cs. Why negative? Because this corresponds to a very small stress state. Now, as we go right towards the right, our void ratio will fall in this portion, which will be less than the initial one. So that's why E critical state ECS is equal to E gamma minus Cc log of sigma dash Cs. Fine. So ECS and E dash correspond critical state, and E gamma is the void ratio at sigma is equal to 1 kPa on critical state line. Now this phi dash Cs, E gamma and Cc, they are the fundamental soil properties. They are not going to change. Now apart from this, here we consider the void ratio, correct? The similarly we consider the volumetric strain in terms of void ratio. Now there is another way of doing it. We can consider the volumetric strain in terms of specific volume. This is one relation then that we can have between the E versus E critical state, E gamma and sigma critical state. Fine, in which we have considered the volumetric strain in terms of the void ratio, and this is the relationship between the stress and between the stress parameters. Fine. Now, in terms of specific volume, how it looks. For example, this is the initial state at O. Then we have done the consolidation. Fine. Now, during the consolidation, there will be a volume change. At C, we have unloaded the sample to B. From B, we are reloading it to C, and from C, we are again loading it as usual. So this portion, where we are doing the unloading case, this unloading, it will be this portion will be relatively stiffer because it is a OC state. In the OC state, our soil will be having a stresses. It has experienced the stresses more in the past than the present. You can see that this is the yield stress for this portion of the soil. So whatever the stress it will be experienced, it is less than the stresses it has achieved at the A state. So it means that this will be it will show a stiffer response and elastic. So at any point of the curve, we can have a bulk modulus given by d p dash divided by change in the stresses divided by change in the volumetric strain. So change in the effective stress p dash or and the change in the volumetric strain. Now since like you can see that the change in P and the change in volumetric is not constant at any point of time. So they are changing throughout the test. So it means that K dash parameter is not unique to consider. It's going to change. Now again, we will take the same plot. We will use a logarithm variation in order to derive the parameters and to account for the large stresses. For example, again, the same exercise, P is equal to 1 kPa, the lowest stress we will consider, and corresponding to P, the specific volume during the reloading that a soil can have is Vk. Just a second. Okay, the broadcasting has stopped. I have to log in again. Just a second, give me time. Actually, lag happened. So where from the lag started, so I can start from there only. From this slide, volume change behavior in terms of. Okay, fine. Yeah, just a recap so that I can get inflow. So in this slide, we saw how the critical state parameters we can how we can define the critical state parameters in terms of volumetric state, but when we consider the specific volume. Now we will develop the relationship as we have seen earlier. So you can see this plot between the P dash and volumetric strain. It is similar, uh, like P versus E. Now what we are doing, we're simply it should be E versus P or specific volume versus P. Fine. Similarly, we are doing it like we are plotting the specific volume versus P. Same things like this is the initial condition. So our P will start from this point where the volumetric strain will be very minute initial condition. Then with the start of the test, what will happen that P will start to increase, our mean stresses will start to increase, and this volumetric starts to increase, or like it depends. Like, if we are doing the consolidation and all, it will start to increase. Now during reloading, what will happen? There will be some regain, or we can say there will be the increase in the slight increase in the void ratio or the specific volume. Later on, when we start unloading it, there will be again some decrease in the void ratio, since this part will it's a kind of uh, a stiffer behavior, or it will show a OC behavior. As a result, it will be kind of elastic, so the rebound will be at least not, there will be no difference or very minor difference between the stress like the stress states or the void ratio between these two points. Fine. And that's why here we can see there is a straight line, because there will be very minute change. And once it reaches the C, it will join the normal consolidation line again. So A and C can be considered as the yield stresses. Now, for if we take the logarithmic variation for the linear curves and to account for the large stresses again. So if we start developing the relationship between the effective like the P dash, which is the mean effective stress, and the specific volume, let's assume we'll take the very small amount of stress 1 kPa, and corresponding this 1 kPa, we have the initial state uh, as n naught, correct? Which if we like the state starts from O, but we have just interpolated it backwards and got the state n naught. Fine. And now this corresponds. This is a kind of a specific volume at 1 kPa. Fine. Now from O to A, when we are doing the consolidation, or when we are doing the loading, it will following the normal consolidation line NCL with a slope of lambda. Lambda, please remember that there in the E versus log P it was CC. Here we have a lambda, which represents the slope between the specific volume and log of P dash. Now from A, we have started unloading it and then again reloading it. So this P is equal to 1 kPa. At P is equal to 1 kPa, the Vk represents the specific volume corresponding to this reloading at 1 kPa. Fine. And then again we have started loading, and from C to D it will again follow the normal consolidation line. So line OACD is normal consolidation line whose slope is given by V is equivalent to N naught minus lambda times ln of B dash. Correct? Fine. Similar, like same as the previous one. And line ABC, it's the swelling reloading line. Swelling reloading line. Swelling reloading line with the equation given by V is equal to Vk minus Kn ln of B. Fine. This slope K, it's not K, it's a kappa, which represents the slope of the swelling reloading line. And P dash is the effective stresses or mean effective stresses. So you can see that how the representation between the E and specific volume is different as like how they differs. You can see how they differ. Here it is Cc log of sigma dash, and here it is n naught minus lambda times ln of P dash. It's not E here. It's ln of P dash similarly here. Okay. This lambda corresponds to slope of NCL and kappa is the slope of swelling reloading line. Fine. Now this parameter lambda, kappa and n naught, they are soil parameters and depends on the soil type. How the soil will be. If it is loose and dense, how this slope is going to change. So these are also not fundamental properties of the soil. They are going to change as the soil type. Soil can be unloaded from any point. This is true. Like we can start unloading the soil from here, from here, from here, from here, from here. It means that this parameter Vk is also not a fundamental property, and this also Py, it's also not a fundamental property. They are going to change with the with the intent where we are going to reload or load the sample. Now, for relating the specific volume to the stress history, we can have this. We know this equation: V is equal to n naught minus ln of P dash. This equation correct? Now, if we differentiate it, fine. dV is equal to n naught minus ln of like differentiation of ln is 1 by P dash. So dV by dP dash is equal to minus lambda divided by P dash. Fine. So dV by V is equal to lambda by Vp dash dP dash. So similar, well, like what we are doing here, we are simply multiplying the denominator of both sides by V, because we want to arrive at the equation where we can replace the whole this term with K dash. Why we want to bring the K dash K in the equation. So once we are doing it, we will get dP dash divided by d volumetric strain is equal to Vp dash divided by lambda. This change in the specific volume to the like initial specific volume will also give a idea of a volumetric strain. It is equivalent to the idea of volumetric strain. So this term is equivalent to the bulk modulus K dash, which is given by Vp dash divided by lambda. So this is the bulk modulus equation for the for NCL, for this line, NCL line. And for reloading, swelling reloading line, we have the equation Vp dash divided by Vk. Now, as we are talking about the critical state, when I talk about the critical state, that critical state is a final state or a constant state the soil can achieve, beyond which we don't expect any state. Now that can be defined from these plots also. Like this NCL is a normally consolidated line. What is normal consolidation? If I talk about what normal consolidation, we have two states: OC state and NC state. Normal consolidation and normally consolidated state and or consolidated state. Now, normally consolidated state means that whatever the stress the soil is experiencing, it's experienced first time. Fine. So it means that, for example, let's assume do it. Let me show it here. For example, I have taken the soil. Fine. I am loading it. Fine. So I have the A versus log P. Log P. Fine. So when I start loading it, the void ratio at the critical state and the P at the critical state, or once you start, where it has start once like at the final state when it is a critical state, that P or that mean effective stress is the state of the soil which it has achieved in a current time. Fine. Like I'm loading the sample, I'm recording the values. So this, for example, I got this point. Fine. So this stress state of soil is experienced for the first time. Fine. Now, second time I started the test, I got some other thing. Like I got E versus log P with this this point I got. Similarly, I got this point. So this line is representing actually the path of the soil based on its initial conditions, which it can follow when we are doing the normal consolidation. It means that if we are telling, okay, for this soil, for example, it was soil A, is it possible that uh, we can have a state like this or state like this? No. Why? Because this is the stress the soil is experiencing in the current time, and at the same time we can't expect a state which is going beyond this or above this, right? And above this CSL, critical state line. So it means that on the right side of the critical state line, we can't expect any state. We cannot expect any state beyond this line. Beyond this line, we cannot expect any state. And below this normally consolidation line, below this normal consolidation line, what will happen? That we are doing the loading unloading, and when we are doing when we are doing the loading and unloading cycles, it means that we are reducing the stresses in the soil. We are experiencing this. We are imposing the stresses on the soil which are less than what it has achieved at A, what it has experienced at A. So it means that this state represents the OC state, and this part OC state, as you recollect from the previous lectures, it is a stuffer state. It has a lesser bound. Like this state used to be a kind of a elastic behavior. And if we talk about the OCR, over consolidation ratio, for this point, like for this line, it is given by Py, which is the maximum stress it has experienced, right, to the present one. Present is P dash B. You can see P dash Y is greater than P dash B, because from here we are doing the unloading. So current state of the soil is the OC state, because the present stresses are less as compared to what it has experienced in the past. So from here, if we see, this is the state. This is the state where I would say, like, for at A the stresses are P dash Y, or pre-consolidation stress is P dash Y. So can we say that this this state is can a soil achieve a state like this point? No, because this is the maximum stress the soil is achieving now in the present. Because if we talk about this point, this is the stress the soil is achieving at present. So this becomes our impossible state. We can't expect a state, or we can't expect any stress or the state of the soil above this NCL. Right? This is the final NCL line, is actually the line which shows us the current state of the soil. What is the current stress state of the soil? Above it, we can't expect any state of the soil. Now we are relating after that, in order to study the effect of the stress history OCR on the plots, and how OCR becomes a meaningless parameter in some cases, and why we want to go into a new parameter that we call the yield stress ratio. So at some point of time, this OCR can be a good parameter to analyze the stress states, but at some point of time, this OCR becomes obsolete, and we need some other parameter to describe those states. So in this, OCR and yield stress ratio, we are going to describe one scenario where we need a new parameter, called the yield stress ratio to describe the stress strain, or to to determine or to define that phenomena that's occurring. For example, we have considering two points P and Q, this P and Q with the same OCR. So OCR for this and this is same, correct? So OCR of P is P dash YA divided by P dash P, and OCR of Q is P dash Y divided by P dash Q. P dash Q is the current state of stress for point Q, and P dash P is the current state of stress for P. Now, similarly, we are doing the long things for just for elaborating the equations. Now the thing is, like, if we have the same OCR, it means that they should have a same consolidation stresses. Now these 2 points cannot have a same OCR. Like, for example, that if these 2 points A and Q are considered, they have the same P dash, correct? They have the same P dash, correct? But with different stiffnesses. Why? Because A lies on the NCL. It has a lambda. It has a stiffness corresponding to lambda, and this Q lies on the swelling loading line, which has a slope of kappa. Correct? So their stiffnesses will change. This will have a high stiffness as compared to this. Now, point B and Q have nearly same specific ratio but with different stiffnesses. See, now this B and Q, again, point B and Q have nearly same specific volume, correct? But there again the stiffness will change because this lies on NCL and this lies on the swelling loading line. Fine. Also, this A and B will have different stiffnesses corresponding to loading and unloading. Now, this A and B can have different this can have different stiffnesses. Why? It depends upon how much loading and loading cycles you are doing between these 2 points. Fine. Now, why this is important? So it means that soil stiffness is not only dependent on the specific volume and the mean effective stress, but also on the lambda in K, or sorry, kappa, depending on the loading and unloading conditions. So the stiffness of the soil will not be judged, or we can't say that based on the specific volume and P dash our soil stiffness is this, but it also depends upon how and how many times or how much loading or loading we are doing, which can affect the soil stiffnesses. Now point P can move to Q if we take this point P, and if we want this P to reach point Q, it has to do first loading. It's a swelling like reloading from P to A, then loading from A to B, then we have to do swelling from B to Q. Fine. Or what it can do, we can simply reach from here by decreasing the stresses. Now the thing is, uh, since I want to like introduce to you a concept of creep, which is actually the volume change that happens at a constant stress. Fine. So this PQ will not be a good points to discuss the creep, but A and Q will be the kind of a good points to help you understand the creep. What creep is? Creep is actually the volume change that occurs at a constant stress. So you can see there is a change in the specific volume between points A and Q, and also between these points the stress is remaining same, that is P dash Q. Now for this A and Q, for this A and Q, while A is directly moving to Q, like it's going from A to Q downward direction, P dash YA is equivalent to P dash Q. P dash YA is equivalent to P dash Q. It means that our OCR will become 1. There is no change in the P dash. Correct? So OCR for this state, like for see, OCR is present by past like pre-consolidation stress divided by the initial stress, the current stresses. Or pre-consolidation stress is P dash YA. Now and present stress is P dash Q. Both are same. They are lying on a vertical line. So delta P dash is 0. So it means that OCR doesn't represent the state of the soil adequately for the creep. That's why we are moving towards the yield stress ratio. That's why we are moving towards the yield stress ratio. So state of soil for this condition of creep can be better understood by the yield stress ratio. What is yield stress ratio? It is the ratio of the yield stress which represents the stress at the intersection of swelling line through Q with NCL. For example, this is the point of our consideration. Fine, we have these 2 points. So we want to know the yield stress ratio. It is given by P dash Y. P dash Y is equivalent to the yield stress, which represents the stress at the intersection of the swelling line through Q with NCL. So we had to draw a line through Q, and when it touches this normally consolidated line, NCL line, which it touches at B point. So the yield stress at this B is P dash YB. So it will be equivalent to P dash YB divided by the current stress. Current stress is P dash Y or P dash Q. So you can see that when we were talking about the OCR, we were actually neglecting this yield stress at B. So the soil can reach this creep state either directly going from A to Q, or it can come from A to B, B to Q. So if we are talking about OCR, the information corresponding to B was getting like neglected. But when we consider the yield stress ratio, it is actually taken account this B state also, which is represented by which is actually the which is accounting for the stress at B also. So the soil state of creep can be better redefined by, or we can say it is defined by yield stress ratio than the OCR given by this equation. This is the basic equation, and this equation is corresponding to Q state. This helps to understand the condition like creep in a better way. Yeah. So like if we talk about creep in terms of OCR, we will get a one value. It doesn't tell us anything about the stress rate of the soil. But when we talk about the, and also like we are actually nullifying the information corresponding to B state from where this Q state has reached. Like once A starts loading to B, and then it has gone the unloading from B to Q. So in the OCR, this information was missing. But when we talk about the YSR, the yield stress ratio, the information corresponding to this state is not getting like nullified. It's taken into account. Fine. So this all content we have seen in the week 9. Now we will do some example problems. So these example problems are like just these are very similar to the ones that you will observe or you will see in the assignment problems. So we'll start doing it uh, after 5 minutes. So after 5 minutes break, we will start doing example problems. So we'll start the example problems. So they are not going to be very long. They're short as per the. So we are going to start the example problems. So they are not elaborative or long question answer type. They are very short and they are as per the assignment problems. You will get a similar assignment problem like this. Once you'll be able to solve here, you'll be able to solve the assignment problems very quickly and properly. So question number first is a normally consolidated clay sample at a depth of 4 meter has a void ratio of 1 and specific gravity of 2.7. Presume that water table is at the ground surface. Determine the lateral effective stress at the rest if phi is 32 degrees. So it's a pure question from the week 5, 6, 7 that we are discussing. Why we want to discuss this question here also because we have the cases for like the initial case for the stress representation for the field case second. We need this information for determine the lateral stress and all. That's why you will see a similar question in the assignments also. That's why I started with this question. So first we'll start writing down the information. So normally consolidated clay at a depth of 4 meter has a void ratio of, so it has a void ratio of 1.0. So you can consider it like it's the ground surface. And we have soil element here at a depth of 4 meter. Fine. So water table is at the ground surface. Fine. And it is given phi is 32 degrees. G is 2.7. Fine. So first of all, it's required to determine the unit weight of the soil. It will be a submerged unit weight because water table has a ground surface and we are to deal with the effective stresses. So gamma dash is equivalent to G plus E divided by 1 plus E gamma W minus gamma W. Fine. So gamma W we can assume as 10. So I will write gamma W is equal to 10 kPa. Sorry, not 10. 10 per meter cube. Now G given as 2.7 plus 1.0 divided by 1 plus 1.0 into 10 minus 10. So unit weight 2 plus 3. I have a calculator. I will do it on the calculator. So you will get it as 8.5 kilonewton per meter cube. Fine. Now at this depth, what will be the submerged? Like what can be the stresses? The unit weight corresponding to this stress state. Like for this sample which has been taken from 4 meter depth. So sigma 1 dash will be equivalent to 8.5 into 4. Fine. That is 34 kilonewton per meter square. So why this sigma 1? Because for this sample the loading will come from top on. Fine. Now for the lateral effective stress at rest, phi is given. So phi is 32 degrees. We know that K naught is equal to 1 minus sine of phi. Rather we can write it phi dash. So 1 minus sine of 32 degrees. So 1 minus sine of 32 degrees is 1 minus sine of 32 to 0.47. It's K naught. Fine. So we know that K naught is given by sigma horizontal by sigma vertical. Fine. So implies sigma horizontal is equal to 0.47 into sigma vertical is 34, which is equivalent to 15.98 kilonewton per meter square. So this was the question. We had to determine the lateral effective stress at rest for the condition where the soil sample was at a depth of 4 meter from the ground surface and water table was at the ground surface. Fine. Now another question. The soil is isotropically consolidated at 150 kPa. Fine. The inclination of ESP is 35 degrees with the S dash axis. The inclination of failure line is 28 degrees. Determine TF. So we have been asked to determine the final final TF, which is a stress path parameter. So what is given is, for example, we have a soil state. This is S comma S dash and this is T. Fine. So this is the equation of the failure line, or like the failure line is inclined at an angle of 20 degrees. And we have been asked that TSP is inclined, the inclination of TSP is 35 degrees. For example, it's like this. (35 degrees TSP). Fine. So we have been asked to determine the TF, final TF or stress path parameter TF, and we have been given that the soil is isotropically consolidated at 150 kPa. Now we know that at initial state, sigma 3 dash 1 is equal to sigma 1 dash, which is equal to 150 kPa, right? For an isotropically consolidated specimen, correct? So S naught dash is equal to sigma 1 dash plus sigma 3 dash divided by 2, that is 150, and T naught dash is equal to sigma 1 dash minus sigma 3 dash divided by, which is 0. So our first point comes out to be 150 comma 0, correct? Now using this, the relation between the T and S, our T final can be written as T final is equal to, like for example, I am telling due to the loading, if S naught and T naught are the initial points, due to the loading it has the final state is SF dash and TF dash. TF. This is the change that has occurred due to the loading. Now, this change from initial to this state, from the consolidation state to this state, it will follow a relation. What is the relation? T by S. Like if we know the slope, slope of this T by S is equivalent to, what is the slope of this line? It's given by tan of tan of 28 degrees. Slope of this line. Fine. So it means that this is one equation that we will use. The slope of this line, T, slope of this failure line, AFC, is given by T by S. So we can write T final is given by SF dash final tan of 28 degrees. Correct? Final state TF will have some relation with the SF dash, which is given by T is equal to SF dash tan of 28 degrees. Apart from this, if the ESP has an inclination of 30 degrees, 35 degrees, 35 degrees with the S0 dash. So for slope, this is SF dash TF dash TF. For this slope, for this point, so again we can write an equation that for ESP, based on the ESP inclination of 35 degrees, we can write the change in the S and change in the T can be related to the slope of this E, and like I can say delta T by delta S is equal to the slope for this ESP line. Fine. So what is the change in T? So the change in T is TF minus T naught can be written as SF dash minus S naught dash tan of 35 degrees. Correct? So this is equation A, this is equation B. Fine. So this is the equation of a failure line which relates the failure stresses. Like the final, we can like the failure stresses. Now this TF and T, this equation, this ESP is an inclination of 35 degrees. It relates the particular soil state, and let's assume that the final point where this TF, TS and SF lies, it's on the failure line. Fine. So it means like once we'll extend this to here somewhere, so this will reach there. So our TF and SF will be on that point, at that point of intersection. Correct. Now we have the equation of TF in terms of S and T naught is 0. Can we put TF is equal to SF dash tan of 28 degrees minus T naught is 0. SF is SF dash minus S naught dash tan of 35 degrees, and S naught is 150. So you will get SF dash is equal to S naught dash tan of 35 degrees divided by tan of 35 degrees minus tan of 28 degrees, which is equivalent to 150 into tan of 35 degrees divided by tan of 35 degrees minus tan of 28 degrees. This is equivalent to 638.34 kp. So the main thing is you are relating the T and S at failure based on the slope of the failure line, and you are relating the T and S based on the inclination of the ESP. Maybe like if we extend this, it will meet at here, at which our TSP and ES and our T and S parameters will be related by two equations, one by this and one by this equation. Fine. Now another question is it's very easy. Specific volume of soil on NCL is 2.05 at P dash is equal to 100 kPa and 1.92 at P dash is equal to 300 kPa. Determine lambda. So we have that equation. We have V here and P here, P dash here. We have that equation. What is that? Uh, I have forgotten actually. It's somewhere here. Yeah, V is equal to N naught minus lambda times ln of P dash. So we have the equation V is equal to N naught minus lambda times ln of P dash. Fine. So the first point lies here at 100 kp and another is at 300 kp. We have to find the lambda. That is the slope of this line. So we write V1 is equal to N naught minus lambda ln of P1 dash. So V1 corresponds to the specific volume at P1. So we can write as 2.05 is equal to N naught minus lambda times ln of 100. This is A, and another is 1.92 is equal to N naught minus lambda times ln of 300. So if you subtract and then do some readjustments in the equation. Oh, okay. Yeah, one thing I just saw it. In this question, we have been asked to determine the TF, correct? So we have stopped at TS only. I apologize for that. So TF SF we determine from the by assuming the value of TF is equal to, not assume, but by replacing replacing the value of TF by SF dash tan of 38. So if we put back this SF dash back in the TF, we will get the value of TF. So that TF will be equivalent to 638.34 tan of 20 degrees. You can put the SF dash in this equation also. You will get the value of TF. So T at failure, that's what I mean asked. We have to determine the T at failure. So T at failure will be equivalent to 638. 638 is 623.34 kPa. Similarly here 623.34 into tan of 28 is 0.5317. You will get 331.37 kPa. Please check this value once again. So thing was, like, we can plot it here more properly. It's telling us that you have a stress state where the failure line has an inclination of 28 degrees. Let's assume it is 28 degrees, correct? You have S dash, S plot, and T, correct? Now, somewhat your ESP has an inclination of 35 degrees. So 35 means it will be somewhere like this. It's very curved, like this. So it will meet somewhere here. So this was 35 degrees. Fine. So this is given 150, 0 is the initial state of soil. Now this was S naught dash T naught, and this corresponds to SF dash TF. Now the relation between the T and S, we can do it by two ways. By relating the this is a KC, by relating TF is equivalent to SF dash tan of 28 degrees using the equation of the failure line, and we can determine the TF using the slope of this ESP, that is the change in TF divided by change in the S, or rather not change, we can say delta T by delta S is the slope of ESP, correct? So with these two we will be able to determine this. Fine. Yeah, now this question number 3, the specific volume of soil on NCL is 2.05 at P is equal to 100 and 1.92 at P is equal to 300. Determine lambda. So we'll use this equation. V is equal to N naught minus lambda times L ln of P dash. So we have used this. So just by readjustment, like you can subtract this from this equation 1 from 2. That is 2.05 minus 1.92 minus lambda times ln of 100 plus ln of 300. We can put lambda outside or keep it here. Fine. So 2.05 minus 1.92 divided by ln of 300 by 100 is equal to lambda. Fine. So you will get lambda, which is slope of normally consolidation line, as 0.118, which can be rounded to 0.1. Fine. Similarly, a soil has a specific volume of 1.08 at PDI scale 200 and specific volume of 1.74 at PDI scale 500 at NCL. Find lambda. So again, we can use the same equations where lambda can be written directly as 1.80 minus 1.74 divided by ln of 5 by 2. Correct? 500 by 200 is 5 by 2. So again, you will get a value of 0.065. Which is close to 0.1. Or after rounding, equivalent to 0.1. Now another question is, a soil is isotropically consolidated to 500 to 800 sorry soil is isotropically consolidated to 800 kPa and then reloaded to 200 kPa. The change in specific volume is 0.15. Determine kappa. So it can be you can think it like this. This is the ln of d dash, this is specific volume. So you have a soil so that it's like this. Fine. So you increased this from, let's assume it's a P naught condition, some stress state we don't know. From here you make it to 800, and from 800 it is swelled or reloaded to 200 kPa. It's 200 kPa, and this is 800 kPa. And as a result of which there is a change in the specific volume. That change is given as 0.5. We have to find the slope of this line, or that represents the kappa. Sorry, kappa means k, small k, like this. So we can use the equation specific volume is equal to Vk means kappa times ln of V dash. Again, similar thing. V1 is equal to Vk minus kappa times ln of 800. V2 is equal to Vk minus kappa times ln of 100. Now final minus initial. V2 minus V1 is equal to 0.15. So V2, it is kappa times ln of 800 by 200 is equal to 0.15. So you will get kappa is equal to 0.15 divided by ln of 4, 0.108. So this is the slope of the swelling and reloading. Fine. Now last question. If a cohesionless soil has a friction angle of 28 degrees, fine, pi dash is 28 degrees, and effective lateral stress or effective principal stress or effective minor principal stress is 120 kPa. You have to find the effective vertical stress or effective principal stress or effective major principal stress, whatever. So we know that from the stress mobility equation, sigma stress obliquity equation, sigma 1 dash plus sigma 3 dash is equal to 1 plus sine pi dash divided by 1 minus sine pi dash. So sine of 28 degrees equal to 0.469. So sigma 1 dash is equal to sigma 3 is 120 into 1 plus 0.469 divided by 1 minus 0.469. So sigma 1 dash will be equal to 331.8 kp. So this was the basic question from the civil stress obliquity. So fine. So a brief recapitulation. What we did in this session, we started with some stress path for the field case second, where we discussed about the stress change beneath foundation. So with time, as the pore water, if the failure occurs at P, it means that during the excavation, during the foundation, only during the construction of the foundation, the soil has failed. Or if it happens after some time, if we give some time to the foundation, after it builds up, there is a dissipation of the pore water pressure. As a result, the factor of safety gets increased. Now, yeah, again, one more point, that if once we reach this P dash state, which means that we are subtracting the pore water pressure, initial pore water pressure from the total stress path. So this is the initial consolidation state P dash. From here, if we do the drainage loading, the soil will take the excess amount of load. So there may be the chances that soil can have a high enough of settlement due to the consolidation, or we can say due to the readjustment of particles, which can cause enough settlement in the soil and make the structure service. Can Yeah, sure. I will reach there. I will reach there. Just I will recap these points. So after that we have discussed about the we have discussed about the stress change due to the excavation. So in the excavation, we have two things to discuss. One is either it can be the no, the stress change near the retaining walls. Near the retaining walls, it can be excavation or the filling. So the shearing caused by the excavation is different from the shearing caused by the filling. So retaining walls subject to the excavation. In the excavation, there can be the generation of initial negative pore water pressure, and once it starts to decrease, when it starts to decrease, there is generation of positive pore water pressure, and hence with the time the factor of safety decreases in this case. However, in case of backfilling, there will be the continuous like there will be generation of positive pore water initially, but when it starts to decrease, when it starts to dissipate, the factor of safety increases with time. After that, a general representation of the stress states that we have discussed earlier in the week 8, D1, D2, D3, D4. Then we have introduced you to the critical state soil mechanics, where we have seen that how the critical state takes into account the Morpolo criterion, effect of stress history, where we talk about the OCR and all, stress, soil yielding, the different yielding points of the soil, drain and drain condition. And one more thing to discuss is that one more point which I forgot to tell, that like in the more column thing, more column filler criteria, we have the separate set of like this. We used to define a different stress strain behaviors for the drain and drain case for OC and C state. But here we don't have we can have a kind of uh, unified pattern of this failure patterns, which actually can govern the failure stress or the stress strain response of both the NCOC states and drain conditions. Fine, it integrates the two relationships exist, which it offers a relationship between two D variations, E versus sigma and tau versus sigma dash. And then we introduce you to the concept of critical state. What critical state is? It's actually the state after which once a soil is a critical state, there is no change in the shear stresses, there is no change in the volumetric state, there is no change in the effective stresses. What actually is going there is there is going a reconsolidation at a constant value of stress, which is actually generated, which is actually accumulating the plastic strain in the sample. So since you need a brief like yeah, here you can see that once soil has achieved the peak stress, it's begin to soften. And at this point of time, alright, sorry. At this point of time, you can see this is stress, this is strain. Okay, we can show it. Just give me 1 second, I'll plot it properly. Find the stress strain plot, and I will plot the volumetric strain versus axial strain. This is fine. So I will mark here. So up to here there will be kind of a contraction, then it will start to dilate. Fine. Similar to this, I think in week 8 it will be clear to you here in this diagram. Rather, I will start doing it. See here. You can see in this diagram what happens for the OC soils. After reaching a peak, there will be a softening, correct? And then it will be a constant line. There won't be change in the derivative stress. So if we talk about the volume, this pore water pressure, the pore water pressure, it increases first till it reaches the peak, or the change in pore water becomes negative, means it is decreasing. Fine. So U naught will, it will start decreasing up to this point. Fine. Now after achieving the peak, the U will, it will start dilating this OC soil. And once it start dilating, it will not go in this state. Like it will not start. Okay, I will start dilating. No, no, it will not be like this. It once it start dilating, after reaching the once it reach the critical state, what will happen that this is the kind of it will have a dilation. After that, once state reached, its volumetric strain ceases. And when the volumetric strain ceases, and you can see also here the derivative stress is not varying much. So at a constant stress, at a constant derivative stress and constant volumetric strain, there is accumulation of all this plastic strain, and this occurs due to the reconsolidation or the reconsolidation of the sample, fine, or rearrangements in the sample, which is actually bringing this kind of a this accumulation of plastic strain in the sample, and this state is called the critical state. After which there will be change, there will be no change in the effect this derivative stress, effective stress, or volumetric strain. So the change occurs only in the accumulation of strains. There will be the accumulation of strains which are responsible for like the development of shear bands. There will be like the shear pockets or small zones of failure, which then combine and became a like a visible shear band in the specimen. If you are doing the drain test or drain test, you might have seen this when you are doing the test, drain test. You might see a failure like this. The soil goes like this. This is the initial when you start doing a test, but at the end, when soil reaches its critical state, you might see that this part has failed like this. So this occurs due to the accumulation of plastic strains. So that's why this state is a fundamental state, because this critical state is independent of the initial conditions. Like if you do a, for example, this is uh, E versus time. If you are doing the, if you consider the loose specimen and you are sharing it, what will happen if it is E critical state? Fine. So loose soil will have a void ratio, since it will since void ratio since like in the previous I think week 6 or week 5, loose soil have a tendency to reach the critical state by contraction. Correct. So now what will happen? It will have a void ratio higher than the critical state. What will happen? It will start reaching the critical state by contraction. And dense soils, they have a void ratio less than the critical state. So they will reach the critical state by dilating. Fine. But All the two, whether they are loose or dense, it's E loose and E dense, irrespective of the nature, the initial density, whether it is loose or dense, both these soils will reach the critical state. That is the final state a soil can achieve. Fine. After that, after this discussion over the critical state, yeah, this equation you can refer, or you can remember this for your interview purposes. This one. Specific volume is one other way of representing the void ratio or volumetric strain. And again, this critical state is attained at shear strain greater than 10%, and soil gets reconstructed by the shear strain, as a result of which soil loses the track of initial conditions and achieves a unique critical state. As I told you, that due to the reconsolidation or like it gets rearranged, the particles gets rearranged at a constant stress value at a constant volume, volumetric strain. As a result, it lost its initial conditions, like from which it has come, whether it is a loose or dense, and hence it reaches a unique critical state. Fine. So this critical state can be considered as a fundamental property of the soil. After that, we have developed some relationships among the shear stress, normal stress, and void ratio. Apart from that, the relation between the shear stress, normal stress, and the specific volume. Then this equations we have seen for the like the volume change behavior in terms of the specific volume and the mean effective stress. After that, we developed the equation for the bulk modulus in terms of for this NCL line and the loading swelling loading line. Then we have seen that for some state of soil, like if we have a creep, this OCR becomes meaningless. For that type of behavior, we need a yield stress ratio, which actually takes into account this behavior properly, and we are able to uh, like define this parameter OCR, this creep very properly as compared to the OCR. After that, we went through some example problems which were very similar to the one that you have that you will be seeing in the assignments while doing that. So that was all from my end regarding this week. So if you have any doubts, you can ask in the forum where a proper team of students will be there, tutors will be there for helping you out. And also, like as I told that we have a dedicated mentors in the forum. You can ask the questions, and that will be answered. Meanwhile, you can try the assignment questions. I hope you will be able to solve all those. So if you have further doubts, you can ask. Thank you. I am stopping the recording here. So we'll be meeting on Friday. So till then, like till then, you can check the assignments and all. If you have any doubt, you can ask. So I'm recording the. I'm stopping the recordings here. Thank you.